In this video, we are planning to solve a problem using Hess's law. The intent is to determine the standard enthalpy of formation of methane. We are going to look at the different ways which we can solve it, of which one particular method of interest is by using equations, adding them up to obtain the final required equation and the energy changes associated with it. It's a good idea to know what standard enthalpy of formation represents. H represents enthalpy or heat. The 0 as a superscript represents a standard state. F represents formation, defined as the enthalpy change when 1 mole of the substance is formed from its elements in the standard state or SATP conditions. In this equation, carbon, graphite, plus oxygen undergoes combustion to give you carbon dioxide and standard enthalpy of formation 393.4 kilojoules per mole. Standard implies standard ambient temperature and pressure. If we are talking about ambient temperature, we're going to use 25 degrees Celsius or 298 Kelvin. The pressure we're going to use is 100 kilopascals. Sometimes the conditions are specified at STP. In that case, the temperature would be 0 degrees Celsius or 273 K. And the pressure would be 101.325 kilopascals. For all elements in the standard state, delta H0F is taken as 0. So in a chemical equation, if elements are used, their enthalpies of formation are taken as 0. The values will not be provided, so it's not an error. Here is how you will represent the standard enthalpy of formation. Delta represents change, H represents change in enthalpy here, 0 represents the standard conditions, and F represents the heat of formation or enthalpy of formation. Here is a second definition, and you should be able to distinguish between enthalpy of formation and enthalpy of reaction. When you look at enthalpy of reaction, you would notice that at least one of the reactants would be an element. If both reactants are elements, then we would have standard enthalpy of formation. If at least one of the reactants is an element, is a compound then the enthalpy change is referred to as enthalpy of reaction. And usually when you represent the enthalpy change for the reaction, we express it as kilojoules or joules. We do not use per mole in such cases. On the contrary, when we are talking about enthalpy of formation, all the time the heat change is measured and represented as enthalpy change per mole for the formation of the product. That is critical in distinguishing between enthalpy of formation and reaction, and that should not lead to a confusion later. This equation is read as delta H0 reaction, or enthalpy change for the reaction, is equals to sigma, the sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. Here is an example of enthalpy of reaction. Methane is a compound, oxygen is an element. Therefore, the energy change associated with the reaction is referred to as enthalpy of reaction. Thermochemical equations. When you write equations that include the states of reactants and products and also gives us the energy change associated with it, we consider the equation to be a thermochemical equation. Typical example. Now, these are the different ways in which you can write a thermochemical equations. 3 different methods are shown here. In equation 1, the heat change in the reaction is shown as a product. So, CH4 plus 2O2 giving you CO2 plus 2H2O plus 802.2 kilojoules according to this reaction, which implies that the heat energy is a product, therefore a positive sign. In the second equation here, you'll find CH4 plus 2O2 giving you CO2 plus 2H2O Here there is a comma separating the rest of the equation with the data that's being provided, which we write as delta H, which is actually delta H0 reaction, and it's assigned a negative sign minus 802.2 kilojoules. By convention, when a chemical reaction takes place and the products have lesser energy than the reactants, it implies that the net energy change is the energy that is released during the chemical reaction. And in such cases, the enthalpy change is given a negative sign. So when you're writing delta H is equals to sum of the enthalpy of the products minus sum of the enthalpy of reactants, you will find that the products have a smaller number in energy, or the reactants have a higher number. Therefore, a smaller number minus a larger number will always be negative, and therefore enthalpy changes for exothermic reactions are assigned a negative sign. This is a convention, and you got to start recognizing that now. The third equation, we will see that the heat energy is part of the reactants. So if it is an exothermic reaction, heat is being taken away from the reactants. Therefore, CH4 plus 2O2 minus 802.2 kilojoules, giving you carbon dioxide and water. These are the different ways of expressing the same equation. In multiple choice questions, you may get one or the other form. Recognize the right choice, and that will give you the right answer. So it's a ways of representing thermochemical equations that is being done here. It also implies that 1 mole of methane releases 8.2 kilojoules of energy on complete combustion. And if you actually multiply this equation by 2 and it becomes 2 moles of methane, the amount of energy released would be twice the quantity. Or if you half the equation, the amount of energy released would be half the quantity. Here is a statement for Hess's law. The heat change evolved or absorbed, meaning exothermic or endothermic, in a particular reaction is the same whether the reaction takes place in one step or in several steps. Calculation of enthalpy of reaction. We had seen this equation earlier. Once again, delta H0 reaction is equals to sum of the enthalpy of products minus sum of the enthalpy of reactants. Here in this slide, what we are going to see is how we can represent Hess's law and actually relate it to the statement that we made a moment ago, because we're going to actually prepare carbon dioxide by two different methods. Changing carbon to carbon monoxide using a limited quantity of oxygen, meaning it is an incomplete combustion. So if carbon solid graphite state, in the state of graphite, changes into carbon monoxide, the energy change associated with the reaction is minus 110 kilojoules. Notice the negative sign, meaning this reaction is exothermic. Gives you 1 mole of carbon monoxide. Now you can take this carbon monoxide and oxidize it to carbon dioxide. And the energy change associated with changing 1 mole of carbon monoxide to carbon dioxide is minus 283 kilojoules, which is again an exothermic reaction. So now you have carbon dioxide produced using 2 steps, a 2-step reaction. We also know that you can convert carbon directly to carbon dioxide using a single step with the excess of oxygen. And the energy change associated for that reaction is going to be minus 393.3 kilojoules. Now if you add minus 110 and minus 283, that gives you minus 393. So it shows us the algebraic addition of enthalpy changes during chemical reactions are true based on Hess's law. So step 1, converting carbon to carbon monoxide, plus step 2, converting carbon monoxide to carbon dioxide. When you add the energy changes for the both is equal to the energy change that is taking place when 1 mole of carbon dioxide is forming from its elements. Or we can look at it this way. Let delta H1 be the enthalpy change for the reaction in a single step. Let delta H2 be the enthalpy change for the reaction in which you convert carbon to carbon monoxide. And delta H3 will be the enthalpy change for converting carbon monoxide to carbon dioxide. and delta H1 is equals to delta H2 plus delta H3. So mathematically this is true. So we can use the concept of Hess's law to determine the enthalpy changes of reactions which we normally cannot perform in a lab environment. Here is a question for you. Calculate the heat of formation or enthalpy of formation for 1 mole of methane gas from its elements if the heat of combustion of or enthalpy of combustion of methane is minus 890.0 kilojoules per mole. Standard enthalpies of formation of water and carbon dioxide are given. Now, when you look at this problem, you may want to recognize certain words and terminology and be able to relate them to equations that you can convert them to. So let's look at the first aspect. I would underline heat of formation or enthalpy of formation. And think about the definition that think about the definition that would answer your question. What is enthalpy of formation? It tells you if you write an equation where the reactants are elements and the product is 1 mole of methane, the heat change associated with that is what I'm referring to. Now the second data that is provided is called heat of combustion. You're going to determine enthalpy of formation from heat of combustion. Underline that. Heat of combustion means methane is going to undergo combustion or a reaction with oxygen to give you carbon dioxide and water, and the heat change when 1 mole of methane is used is going to be 890 kilojoules. That's the second information that you should take from this statement. Then you're given 2 more numbers and they are associated with definitions: standard enthalpies of formation of water and standard enthalpies of formation of carbon dioxide, which means water is formed from its elements and carbon dioxide is formed from its elements, and the energy released when 1 mole of these substances are formed are provided for you. So you're going to use all of this information to actually solve the question. Let's see how you can do it. Once you solve it, the answer to the problem is going to be around minus 75.5 kilojoules per mole, and we will see how we can attain this. Every time you're trying to solve a problem relating to enthalpy changes and where we are trying to find out the enthalpy change for a certain reaction, the first thing to do is you need to write what we call a required equation or a target equation, which means the enthalpy change represented for that equation is what we need in the problem. In the given problem, it is a formation of methane, or we are looking to find the enthalpy of formation of methane. So the required equation will be written like this: carbon solid plus 2H2 gas giving you CH4 plus delta H0F, where heat of formation of methane is what we need. So this is what we do. The first thing to do would be to generate equations for all the given data. 3 separate sets of data is provided to us. One is heat of combustion, second is heat of formation of water, third is heat of formation of carbon dioxide. Now we are going to change those statements in equations. Heat of combustion of methane would be CH4 plus 2O2 giving you CO2 plus 2H2O plus the heat energy released as given in the data. The second equation would be H2 plus R4O2 giving you H2O when 1 mole of water is formed. That's the second equation. And the third equation is C plus O2 giving you CO2. So we have just identified the 3 reactions. In the second equation, discard the positive sign that is written after H2O. Now in the target equation, we need 1 mole of methane. And we have to use these 3 equations so that we can obtain the required target equation when we add the 3 equations together. Notice that in the enthalpy of combustion, that is equation number 1, when complete combustion takes place, 1 mole of carbon dioxide is formed and 2 moles of water is formed. So we need to know the heat change associated with the formation of 1 mole of carbon dioxide and 2 moles of water. So the data was provided for 1 mole of carbon dioxide and 1 mole of water. In order to obtain the energy released due to the formation of 2 moles of water, we will have to multiply equation 2 by 2 so that it produces 2 moles of water, and the energy released will double. We are going to rearrange the equation so that we can obtain the required equation. The most important thing while rearranging equation is we have the freedom to rearrange the equations so that when we add the 3 equations, we will obtain the desired or the target equation. One of the conditions would be every time you rearrange an equation, we try to pick the reactants and products in the required equation and flip the equations that we have so that we can place them in the right position. There are simple ways of doing this, so we're just going to look at them. One of the important aspects, again related to flipping of equation, would be if an equation is flipped, the energy change is also flipped, which means if you have an exothermic reaction and if you flip the equation, it becomes an endothermic reaction, which leads to the statement, what is flipping? What I mean by flipping is if you change the reactants into products and products into reactants, then the equation has been flipped. So just reversing and writing the equation is what we're talking about while we say flipping an equation. So here I'm going to write the equations in the appropriate terms. Equation number 1 was combustion of methane. Here what I've done is I have flipped the equation. The reason is in the target equation, methane is a product. So if I need to get methane as a product, of the 3 equations given to me, only the combustion reaction has methane included in it. So what I did is I flipped equation number 1 so that methane becomes a product. And when I did the flipping, the minus 890 kilojoules became plus 890 kilojoules. In the combustion reaction, there are 2 moles of water produced. Therefore, again, we did multiply equation 2 or the formation of water by 2. That was the reason. Now, why did you write the enthalpy of formation of water in the same way? We did not flip it here. The reason is very simple. For enthalpy of formation of methane, hydrogen is a requirement. And when I write this equation 2H2 plus O2 giving me a 2H2O, hydrogen is a reactant, so I don't have to do anything. So equation 3 also is written in the same way. Carbon plus oxygen giving you carbon dioxide. And in enthalpy of formation, I need carbon solid, and I have it. Now in enthalpy of combustion reaction, there is only 1 mole of carbon dioxide that is formed. Therefore, I don't have to change the coefficient of that equation. Next thing I'm going to do is add them up together. Now before I add them, I look for common terms on the left side of the equation and on the right side. What I'm going to do now is called adding up of the 3 equations. And what I imply by adding is all the reactants on the left side of the arrow can be written together, and all the products on the right side of the arrow can be written on the right side of the final equation. Now before doing that, if there are common terms on the left side and the right side, I can cancel them out. If there are similar terms on the left side, add them and change the coefficient. The same can be done for products too. So let's look at common compounds on the left side of the reactant and the right side. Carbon dioxide on the left, we have 1 mole. Carbon dioxide on the right, there is 1 mole. So we have cancelled that, crossed it out. 2 moles of water on the reactant side, 2 moles of water on the product side, that's cancelled out. On the reactant side, now I have 2 moles of oxygen. First mole of oxygen is coming from the combustion of hydrogen, and the second mole of oxygen is coming from the combustion of carbon dioxide. So we have 2 moles of oxygen on the left side on the reactant side. And we also have 2 moles of oxygen on the product side, so it's totally cancelled out. What remains is carbon plus hydrogen giving you methane. That is the target equation that we were looking for. So when we sum up the values of the enthalpy changes by applying appropriate signs, the net resultant enthalpy change is minus 75.5 kilojoules, and that's the enthalpy of formation of methane, and we have the required equation. And that's how you solve a Hess's law problem. Review the problem if you like it. Don't forget to rate, comment, and subscribe to this video. Thank you and have a great day.